So the topic for the day is MPLS. Okay. Though we don't have this to be covered in detail, the Cisco CCNP NRC ask for some described kind of thing, only theoretical topic. But we will do a lab and we will see how MPLS work. But I would like to know how much you rate yourself out of 10 on this topic. So are you familiar with MPLS, or this is your first class for this topic? Okay. Okay, fine. It's not an issue. Not an issue. I'll go ahead with the basics first, okay? And then we will do a lab. MPLS. The full form of MPLS is multi protocol label switching. Okay. All right. So the topic, as I told you, it's MPLS for the day. Multi-protocol label switching, and the important thing about this technology is your packets are now labeled. Okay, labeled in the sense they are labeled with a numerical labeling, say for example 17, 16, 18. Now why do we do this, where do we do this, is something which we are gonna learn today. Okay, so let's assume this is my ISP cloud where I have couple of routers in the ISP side. Okay, and I have multiple customers. Let's say customer A. Similar way, let's say I have customer B, and on the other side, let's say the customer A wants to communicate to the customer A branch office, and similar way I have my customer B. So let's say this is headquarters and this is the branch office. So what do you think will happen? So let's say this is ISP. ISP is nothing but the internet, right? So whatever packet you send, the packet will hit this. So this router is called as PE, provider edge, and this router, which is kept in the customer premises, we call it as customer edge. Okay, so the first packet will hit this PE. PE will forward it to one of the IBGP router, because we know that they are all running over on BGP protocol. So over here we have eBGPs. The same goes over here. We have eBGP, external BGP, and internally they are all connected over IBGP. Okay. Now what happens is your packet number 1 hits the first IBGP. The second router will now forward it to the another IBGP. Okay. Then it sends to one more IBGP, and then finally your packet goes out of this towards the customer A. Now problem with this kind of approach is, if you see it in a simpler way, that the whole concern here is just to send the traffic from customer A to customer B. That's the whole motive of this particular design, right? Don't you think what is happening right now is, from the PE it went to some router, from that router it went to something. So basically we are increasing the overhead on these devices, the devices which are kept in the cloud. We are increasing the overhead on these particular routers which are in the ISP. Okay, and also you know that ISP consists of 80 lakhs of prefixes. Okay, and if you have, let's say, 30-40 prefixes, your individual prefixes will be forwarded from one IBGP to another IBGP, and finally it will come out and it will go to the customer A on the branch office region. So there are a couple of concerns now in the case of the internet or in the cloud. If we don't go with this kind of technologies like MPLS, uh, we will be, and we are just trying to exhaust those routers which are kept in the ISP end. Okay, so we are increasing the overhead. The prefixes will be keep on increasing, right? So the prefixes gets learned on every routes now, right? So there are couple of issues with this kind of design. So we have some approach where we can minimize this by using something called as route reflector. Okay, route reflector, or uh, we also have something called as route configuration. So these are all technologies to select one router act as server and the rest of them act as just a client. Okay, but the problem with BGP is they prefer route recursive lookup. Okay, so basically what is route recursive lookup in BGP? It's something where the BGP, while sending it to some destination, let's say destination 4.4.4.4, what it does is it does two times lookup on its routing table. The first would be how to reach the gateway, and then it comes back to see once again the routing table to see what is the shortest path to reach that destination. So we call this as recursive lookup. Now even if you make use of route reflector, the the concern with respective to recursive lookup will make uh, the whole design to go slower for other customers, like because told you there are 80 lakhs of prefixes here, so one or two uh, might be because of this kind of design the other customers are impacted. So what we do here is, in simpler word, if I somehow can switch my packet, okay, somewhere like on a tunnel. So let's say this is a GRE tunnel. Okay, so where am I creating this GRE tunnel? I'm creating that GRE tunnel between PE1 and PE2. Now what happens is my traffic which is coming from customer A towards PE1 doesn't go to the other IBGP routes. Okay, the moment it hits the PE1, since I have created the GRE tunnel, it will be sent inside that tunnel. It will reach to the PE2 router, and the traffic will reach to the customer. Okay, that makes more sense uh, uh, instead of advertising our prefixes to these IBGP, which will uh, be bombarded with a lot of prefixes already, and also it's increasing the overhead in case we keep on sending the prefixes, right? So we would prefer keeping a GRE tunnel and make it very simple. Similar thing happens here. Let's say this is my P router 1 and this is my P router 2. So let's say I have a GRE tunnel here. So when I have a GRE tunnel, let's say my prefix hits the P1, my traffic enters this tunnel. Okay, it reaches to P1, so other guys are not even bothered or disturbed with my prefixes, and my prefixes straight away go out. Now this is something which we did in GRE tunnel, or I can say we created this uh, design aspect in GRE tunnel, but we know that GRE has some limitation. The limitations are it only supports IP traffic. Okay, now you might have multiple traffic, like you have Apple Talks, right? uh, you have other ways of traffic other than IP, TCP, UDP, VoIPs. Okay, IPv6 traffic. Now GRE doesn't support all of them, and the second limitation of GRE is its header size is very bulkier. Okay, due to the header size, if this is the packet, total packet, if the GRE header is of this size, okay, the data field gets shrinked up. The very less number of data you can send in case of this technology, because of the GRE header itself is bulkier. Okay, now let's say if this tunnel, this particular tunnel was being replaced by something else, some other technology. There are a couple of technology. We have something called as IP in IP or Q in Q, and along with this we have something called as MPLS. Okay, just think in such a way that the GRE tunnel has some limitation. We are removing the GRE tunnel and we are introducing MPLS here. The remaining concept will still remain the same. That is, if something is coming from customer B to the provider H, the traffic will not be sent to the IBGP. Instead, it will be sent over this MPLS tunnel, and it will go to the PH2, and then it will come to the customer. Okay, now that's the concept behind MPLS. Now what happens internally is there will be label added up to this traffic. Why do we add this label? Is the traffic can be for multiple network, for multiple services, right? Might be the traffic is for VoIP. Now the label entered would be 16. If the traffic is for TCP, now the traffic, the label should happen, right? 17. The traffic is for UDP. We say that the label has been added automatically. So these labels will be added automatically the moment you start enabling MPLS technology. Okay, and from the customer point of view, because since we are a enterprise student now, we don't see anything regards to the MPLS configuration on my customer routers. Okay, it's only the service provider engineer who will see the MPLS configuration on the service provider end. So that's why when a when a network engineer who is from the enterprise domain, if you open up your edge router or internet router, you will not see any configuration for MPLS. You will not even know what is happening in the cloud. You are just receiving some BGP prefixes, or you are advertising some BGP prefixes, right? And the opposite side, you have some ISP, might be Airtel, Vodafone, Geo, might be Verizon, AT&T, anything. On their end, they are making use of MPLS, because if they don't take care of their cloud, okay, so if they don't take care of their cloud, due to so many prefixes, the router on their side will be just uh, getting overheaded with lot of prefixes. Okay, so we are trying to make a design where we don't unnecessarily send our prefixes to their IBGP routers, because that's not something is going to help us. Okay, well, so let's do a quick lab. Okay, so as you know, my GNS was not working, so I just did one small setup. I'll give you this lab topology after the class. It's on EVNG. Okay, so I have taken three cloud routers. Okay, so let's say this is a AT&T cloud. On this side, I have customer 1 and I have customer 2. Okay, or I can say this is a head office and this is their branch office. So their traffic from the enterprise point of view, okay, because now there are two things happening here. One is from enterprise point of view and the other one is from service provider point of view. That is why in CCNP enterprise, MPLS is just mentioned as describe. They have not asked us to configure and do the lab, because where is MPLS running? MPLS is running here, okay, more like a service provider. As a enterprise, we are just gonna see what is happening, what does this technology is going to do, okay. So as a enterprise engineers, we are over here, we don't know what is happening in the service provider, but let's do the lab and let's understand what is happening exactly, okay. So this is my headquarter and this is my branch office. So let's say my packet will be sent to the provider edge, okay. I told you the first scenario, the first case number one, where instead of sending to iBGP, I can create a GRE tunnel, right? So we will do that first. I'll create a GRE tunnel and I'll send my packets over here. Okay, I can test it with the help of ping and also with the help of traceroute. Now, as we know that GRE has some limitation, they support only IPs. They are not going to support the other packets. And the second limitation is the header size. Okay, so in the second case is where I'm gonna enable MPLS. Now, what happens is this will be called as my LSR router, okay, or it's a provider ISP core. I can say that that's a ISP core router. This is provider edge, that is nothing but which directly connects to the customer end, and this is provider edge router 2 which connects to the other region, okay. So where are we going to enable MPLS? We are gonna enable MPLS on this router and this router, okay. So I can draw this kind of triangle. We are gonna take out the GRE tunnel. Now the MPLS will be running over here. As a enterprise engineer, you will not gonna see any difference. Okay, you will only see the IPs only. Still, let's say if you're trying to see the latency, you're trying to do some ping test, right? You are gonna ping this IP itself, the other side of the IP. Similar way, if from the other end he's troubleshooting something, he's gonna check by pinging this IP. Okay, so these two guys are not gonna understand what is MPLS on the top doing. Okay, so as a service provider engineer, he will be able to see lot of things that's happening here. The first thing is the moment packet hits the PE router, okay, those packet will be labeled with some numbers. So let's say it is labeled as 16. Okay, now this provider core is gonna build its MPLS table, and this table is gonna show that 16 is meant for this destination 5.5.5.5, and this has to be taken out via this interface fa1/0. Okay, now that is the information that is getting accumulated in this kind of MPLS table. So once the traffic hits this the provider core, now those labels will be swapped. Okay, swapped in the sense now the new label gets added up to that. Let's say 17 got added up. The 17 says that now to go towards 5.5.5.5, go this direction. So basically there will be label switching happening. Okay, we call that as label switching. So first label will be added here. Provider core is gonna swap that label and gonna send to provider H2, and then provider H2 is gonna take that label, because those labels are non-significant from customer end. Because if you send a label packet, basically customer end doesn't know what is the label. The label is happening in the cloud only, or in the ISP core only. Okay, so the provider hand has to remove those labels. So there are certain things that we are gonna discuss. What is swap labels or what is pop. Okay, these are called as label switching in MPLS. Okay, fine. So let's do the lab. Let me enable, or let me start this boxes. Okay, and let me also talk about the protocols that I'm gonna use here. So over here, I'll be using eBGP because they are two different autonomous systems. So the autonomous system on the ISP core is this, and the autonomous system here is this. So basically, over here, it's your eBGP. That's why enterprise engineer, when you log into these routers, you will only see the BGP routes and nothing else. Okay, the rest of the things is happening in the provider end. So in the provider end, we will enable MPLS, okay, and we will enable OSPF so that these routes get learned over here. Okay, and also we will use iBGP between these two routers. Okay, so that the traffic will straight away pass on. So let's see first what happens here. So on provider edge 1, I only have IP address configured and nothing else. I have not configured anything. Okay, so first approach is, first scenario is to set up a proper communication between the customer at 1 to customer number 2 over on GRE tunnel. Okay, right now I'm not gonna enable MPLS. I'm gonna just enable and see the default behavior. Okay, the default behavior of the GRE tunnel. So let's see if I have IP address on all these devices. Show IP in brief. Show IP in brief, exclude unassigned. Okay, so 2 physical IPs and 1 loopback. Okay, customer and 1. So I have one loop. I have one physical interface and 1 loopback. Show IP in brief. And once again, the customer end 2 has 1 physical interface which connects to the provider end and 1 loopback for testing purpose. Okay, fine. So IPs are available. Let's go and enable OSPF here. Okay, now let me configure OSPF here. So let me tell you what are the features or what are the components that we need for MPLS. Okay, we need a IGP. IGP is nothing but either OSPF or EIGRP. We need the chef table. Chef table is Cisco Express Forwarding, which is very similar to MPLS table. MPLS table and chef table, they both maintain some mapping. Okay, that's why we make use of chef table with along with MPLS. In case of MPLS is gonna make a table where it's gonna map the labels. Okay, the labels to the destination network, whereas chef table, it's gonna map IP to the destination IP. Okay, so the chef happens based on the IP to destination IP. MPLS happens, the MPLS table happens by mapping labels to the destination. So these both are like giving a complement to each other in the MPLS technology. Okay, so in this case over here, the chef table is gonna help MPLS to find the next hop. because over here they are straight away MPLS table labeling, right? So the chef table will be seen here, Cisco Express Forwarding. Apart from that, we need eBGP, which will be between customer end and provider end. And then we need to know a little bit on IBGP, which is running over here and between this. Okay, so these are the main protocol that we need here. Nothing else in MPLS. But since we are doing the GRE, we need to know the GRE configuration. But I'm gonna remove the GRE configuration and then bring the MPLS configuration. We don't need both GRE and MPLS. Okay, MPLS is equivalent to GRE. Is that GRE has some limitation? We will remove GRE and then we will bring the MPLS completely. Okay, fine. So let's go to provider edge 1 and let's configure OSPF, and where I can advertise my physical IPs along with the loopback. Okay, so I'm gonna advertise this as well as the loopback. So every router has some loopback. Okay, these are the loopback. So I'm gonna use OSPF for that. So let's say router OSPF 1. So for the first router, it is 192.168.23.0.0.0.255. We can go with area 0, and the second network here is 2.2.0.0.0.255 area 0. Okay, let's go to the provider core, the centermost router. Router OSPF 1 network 3.3.0.0.0.0.255 area 0 network 192. Let me change the modem. Okay, 255 area 0. Okay, and same thing over on the second provider edge. Router OSPF 1 network 4.4.0.0.0.255 area 0 network 192.168.34 area 0. Okay, I have to advertise one more network here, which I have missed it right now. So I go to network 192.168.34.0.0.0.0.255 area 0. Okay, let's look for the two neighborship now. So we have two neighbors now. One is, so where am I checking this? I'm over here. I'm over on this router. So I must have one OSPF neighbor with this and the second OSPF neighbor with this. Okay, that's why 4.4 and 2.2. So OSPF is good. So it is going via the 7-state negotiation. So it will come up. Okay. Now let's create eBGP. Where am I creating the eBGP? eBGP is between the enterprise and the service provider. So here I'm gonna make use of eBGP. Okay, so these enterprise and service provider, they will work on eBGP. So let's go to customer edge 1. Okay, on the enterprise side, let's go to router BGP. What is the autonomous system here? It's 33,000. So I'm gonna say 33,000. What's the command to define the neighbor? What is the IP there? IP is written over here. Okay, So I have taken dot 1 on this router and I have taken dot 2 on this router. Similar way, it's dot 1 here and dot 2 here. If you see your own internet router, you will see the provider is always one digit lower. So they keep dot 1 and they give you dot 2. Okay, so thinking that in mind, I just kept something like that. So let's define that. Let's say 17.5.7.1 and the remote AS of my ISP is 65,000. Okay, this is my customer end, so I'm gonna advertise my loopback also. So my loopback here is 1.1.0 and or let's go with single IP and let's define the subnet mask. Okay, now on the other side, which is provider end 1, let's configure the eBGP. Who is my neighbor? My neighbor is on 17.5.7.2 and remote AS for this is 33,000. Okay, and I don't have any loopback or I don't have any loopback to advertise here because that's been taken care by OSPF. OSPF will do the loopback advertisement. So let's see the neighborship now. Show IP BGP summary. So I have one successful connection now. So this connection is over here. Okay, I can see the eBGP happening here. Now similar way, I'm gonna create eBGP on the other end. So let's go to customer end 2. Let's say router BGP. What's the AS here? It's 55,000. What is my neighbor IP? My neighbor IP is 27.5.7.1. Remote AS here is 65,000. The network over here that I want to advertise is 5.5.5.5 and the mask ID of 255.255.255. Okay, now let's go to provider end 2 and let's configure the eBGP router BGP 65,000. Neighbor is 27.5.7.2. Remote AS of 55,000. Okay, so we should get the BGP coming up. So let's wait. So it has come up now. Okay, so we have the eBGP configured. The next part here is to get the GRE tunnel configured. Okay, we need the GRE tunnels. The GRE tunnel is between provider H1 and provider H2. Let's say if I had no MPLS option, now I would have preferred GRE connection, right? So let's create a GRE tunnel here. So why am I going with GRE tunnel? Don't I have any solution? Yes, I have solution. I can go with iBGP, but I don't want that option or that solution because the moment I send to the iBGP, might be the service provider is having 10 more iBGP peers, right? Let's say he is having 10 more BGP peers. Now my route is unwantedly going all every router and then finally it's reaching to the provider end. So I'm just trying to cut that process. Okay, and I'm preferring to have the GRE tunnel. So that's the step number 2. But the step number 3 would be to take out GRE and bring the MPLS here. Okay, so we are doing the step 2 now. So we are trying to configure GRE and we are gonna test if we can ping from first customer to second customer. So let's configure GRE. So let's say interface tunnel 0. Let's give the source to this tunnel. So let's say 2.2.2, which is the loopback address, and let's define what is my destination. It's 4.4.4. So these are nothing but these are the loopback address on these, if you remember, 2.2.2 and 4.4.1. So that's what I am trying to do now. Okay, I have to mention manually my source and destination. Also, what is my physical IP over on top of which physical interface IP am I building this tunnel? So I have to define that. So let's say it is 192.168.24.2.255.255.255.0. Okay, so basically I have set the address of 24.2. Now that act as my the physical address. Okay, and over here I'm gonna create one more physical address which is in the same network, 24.3/24. Okay, so let's go to provider N2. Let's go to tunnel 0. Let's say tunnel source is now 4.4.4. Tunnel destination is 2.2.2. Okay, and the IP address here is 192.168.24.255.255.255.0. Okay, and let's hope for the tunnel interface to come up. Show IP interface brief. So we can see tunnel is up. Let's check the tunnel status. So we see it's on its encapsulation tunnel. Okay, what else do we see? We see it's a GRE transport tunnel. Okay, fine. So we can see the GRE is up. Now what I've done over here is I just have built a tunnel between them. Okay, but I have not yet configured any IBGP between them, because how is the two router gonna communicate without the physical? Because tunnel is happening on overlay. Okay, where is the underlay? Underlay will be happening on IBGP. Okay, so I'm gonna set IBGP now between P1 and P2. So let's say router BGP 65,000. My neighbor address is my P2, which is IBGP. Okay, so I'm gonna say 192.168.24.4. Now what is this basically? This is something which I have already defined here while setting up tunnels. If you remember this, right? These are the physical address and I am trying to pair them over IBGP, that they act as underlay. The tunnel act as the GRE tunnel act as overlay. Okay, so let's say neighbor 192.168.24.4 remote AS 65,000. Okay, and you know that since this is a IBGP configuration, we need to set the next hop over here. So I'm gonna say next hop self. Okay, because what happens is when the traffic comes from eBGP over here, the hop will be still pointing to this network. It will be pointing to dot 2, but all the other router might lose the connection. Okay, so the best practice is change the next hop so that dot 1 act as the new gateway. So I'm gonna make it as next hop self. Okay, the same configuration will be applied on the P2 as well. I'm gonna say router BGP 65,000. My neighbor is the other side, which is 192.168.24.2, and the remote AS is 65,000, and I have to say next hop as self. Okay, once let's quickly check the BGP configuration we are running between the two provider end. So on the provider end 2, this is what I see. This is the eBGP communication between PE and CE. This is IBGP communication between P1 and P2 in the cloud itself. And this command is for IBGP next hop self. So that the next hop is now P, not not the eBGP thing. Okay, that's a this command applies for iBGP concept. Okay, in iBGP we make use of next hop cells. Now similar way, if I check this configuration for the BGP process, so I have one neighborship with my customer end, and these are the iBGP between provider and provider end. So yes, the communication should happen. Now what are we expecting? If I ping something from here from the provider end, my traffic should not be advertised in the iBGP core. Instead, it should take this tunnel, GRE tunnel, and the traffic should come over here. Okay, and the response will be sent back on this. That's when you have GRE in between. Okay, so let's see from customer end 2 if I can reach my loopback on the customer end 1. So if I say ping 1.1.1, keeping the source of my own loopback is on 1, or I can also give my loopback address itself. Okay, and it's reachable. If I happen to do my trace route, I can properly see how is this path being selected. Okay, let's see what is the path that it's selecting. So it went to 7.1. 7.1 is this. Okay, and then it went to 24.2. Where is 24.2? 24.2 is this. Okay, that is dot 4. This is dot 2. Okay, and then it went to 7.2. 7.2 is this, right? So what does it prove? We didn't bombard our traffic to the iBGP core. We just uh, sent to the provider end, and the provider end to the another provider end. There was a GRE tunnel configured, and the provider end 1 just forwarded the traffic to this. So it was just over on this GRE tunnel. But as we know, GRE has limitation of only supporting IPs, and the other disadvantage is its bulkier header size. We are gonna take this GRE tunnel, and then we are gonna include or involve MPLS technology. Okay, so that's the whole story about MPLS here. Okay, now let's talk from MPLS. What does MPLS support us? So MPLS is going to support us multi-protocol support, which GRE doesn't, and it's gonna have something called as label switching, very important in MPLS. Okay, you might have heard about labels, the terms like labels, all those things, but we are gonna see today how these labels get associated with the traffic. Okay, so this traffic which was originated from customer end, it gets tagged up in the cloud. Okay, why do we tag? Because the traffic can be for n number of services, might be TCP, UDP, VoIP, anything, right? So each traffic in the MPLS cloud is not designated with IPs. We designate it with labels. Okay, so what is multi-protocol in MPLS? That it's going to support IP, IPv6, Ethernet, point-to-point PPP, and frame relay. Okay, these are multi-protocol that MPLS is supporting, which GRE doesn't. And label switching is your forwarding over here, the packet forwarding over here happens on the basis of labels. Okay, purely on the labels, not looking on the destination IP. There is no lookup done on the basis of the IPs. Okay, so if you happen to see, let's say when I am on the enterprise router, if I'm troubleshooting some route, the first thing which I do is I say show IP route 4.4.4.4, right? Basically I'm trying to look up on the basis of destination IP, and I happen to see where is it being forwarded to. But in the case of MPLS cloud, instead of IP, I'm gonna put the labels. I'm gonna see where is this label leading to, which interface is this meant to push the traffic out. Okay, so that's how there are quite a little difference between the normal routing and the MPLS technology routing. Okay, so to get started with the MPLS, what I'm going to do is I'm going to remove those tunnels first. We don't need tunnel now because we know the limitation of tunnel. So we are good with taking out them. So I took the complete tunnel out, and the same thing I'll also do it over here. Okay, so the tunnels are gone. Similar way, the IBGP that we configured between the two providers. Okay, I'm talking about this now. Okay, we don't need this. We basically we don't need both of them, but the moment I remove this will be as good as non-functional, because this is the main command, right? This is not gonna help something because we will lose the neighborship. Once we lose the neighborship, doesn't matter if we keep this or we take it out. So I'll remove this command also. Basically what I'm going to do is I'm going to remove those tunnel, GRE tunnel, and I'm also going to remove those IBGP. Okay, so we will do two things now. So let's go to router BGP 65000 and let's put a no in front of this. Okay, so we will lose the neighborship, but let's also take it from other side to avoid any confusions. Okay, so neighbors are removed, tunnel is completely gone. So you see, the moment I removed the tunnel, the second dependency or dependent line is also been taken down, right? So both the lines are out of the BGP now. Let's enable BGP now. Oh, sorry, let's uh, enable MPLS now. So how do we enable MPLS? MPLS is now on all these three cloud routers. Now this is my core router, ISP core. This is my customer facing. Okay, what do you understand with that? Because in a cloud we have something acting as a core. This core can be connected to multiple customers. Let's say I have a customer for uh, Hero Honda. Might be I have a customer for some other pharmacies. Might be I have some customer who are into uh, some providers or some cable operators, right? So core is your main ISP router, and these are the provider end, and we call provider end the router which face directly to the customer. So this could be a provider end for the Honda customers. This could be a provider for those cable operators. There's one more provider router here which is for the pharmacy. Okay, so we need a core here. So this is core, provider end, provider end. I'm gonna implement MPLS, MPLS, and MPLS here. Okay, these are service provider command. No changes to be done here. We have done enough number of changes. We have configured BGP over here. That's enough from custom from the enterprise level. We are gonna do MPLS only in the cloud now or in the ISP core. Okay, so let's go to those interface. This is a interface level command. So let's say interface f0/0, and I'm gonna say MPLS. If you see this, configure dynamic MPLS, I'm gonna say MPLS IP. The same thing will be put up in the provider end 2, FA1/0 MPLS IP, and there will be two commands, two interface which will act as MPLS, one towards P1 and the other one towards P2. So I'm gonna say interface F0/0 enable MPLS IP, and its second interface, which is F1/0, enable MPLS IP. Okay, the moment I did that, I got some syslog messages saying LDP has been enabled. Now this is the route, this is the label switching technology happening. Okay, this is nothing but label switching happening. Okay, label switching. Now what we need to do is we need to create IBGPs now. So where am I gonna create IBGP? I'm gonna create IBGP between my tunnels, my loop back. So let's say this is over on 44444, and this is 2.2.2.2. Okay, so I'm gonna build IBGP between this to this. Okay, so there will be one IBGP. You can take out the GRE now, we don't need GRE. Okay, we are gonna build IBGP over on loopback. Earlier I built IBGP over on the tunnel IPs, but now I'm gonna take the loopbacks. Okay, so let's go to P1. Let's go to the BGP process 65,000. Let's say neighbor now is 4.4.4 and the remote AS is 65,000. Since we are making use of loopback, we are gonna say update source on the loopback. Okay, and I'm gonna make it as next hop self. So this is a special command when we build a IBGP or eBGP basis on the loopback. If I don't do this, the TTL value or the multi-hop, the scenarios of multi-hop, you're aware of those concepts. So those will come in, and then basically they will not form neighborship. So we have to make use of this update source. Okay. So similar way, I'll go to provider N2. Who is my neighbor? My neighbor is 2.2.2 and the remote AS is 65,000. 2.2.2 is gonna update over on loopback 1, and then the next hop self. Okay, fine. So I have done MPLS configuration and I have done IBGP between two providers. We are done with MPLS. There is no difficulty in configuring MPLS. The only the technology and the hypes about MPLS is the reason why a lot of guys think that MPLS could be very difficult. But this is just from CCNP enterprise level. But yes, when you go to the service provider, there are a lot of things that happens here. But from enterprise level is enough. It's good enough, to this extent. Okay. Now, how do I check if I have successfully configured and if I can reach from one customer end to another customer and what is happening in the back end, right? So we have to verify, right? So if I do show MPLS forwarding table, you see there are some labels happening. So these are labels 16 and 17. So they are the labels which gets created automatically. But yes, these labels can be changed. We can say that for an MPLS, the label should be created in the range 100 to 150. Now, when you set that command, the labels will come in that particular range, like 100, 101, 102. But as a default, if you have not set that particular range, it will start from 16. Okay. Now let's try to ping first. I'm gonna ping my customer end 1 on my loopback 1, so it's reachable. If I do a trace to the same destination, let's see which path is it taking. So it went to dot one. Dot one is this. Okay, it got no response here. That's because this is now working on labels. Okay, and it went to 23.1. Where's 23.1? 23.1 is this. Okay, from 23.1 it now reached to dot 2, and the loopback was directly connected. So my traffic went over in this direction. Okay, now it's not about longest path and shortest path here, it's about the technology. Okay, we are trying to minimize those unnecessary IBGP involvement in this cloud. Okay, so you might be thinking, in the previous case it went straight away over GRE, now it went one more hop ahead. We are good with that, we don't have any problem here. It's not about the shortest match, it's about the technology and the overhead and all the other issues that you would have gone through if the IBGP would have been the first preference of routing. Okay, in case of IBGP, let's say if you had more routers here, they are all IBGP. Now the moment you the provider end receives some routes, it would have advertised to all the IBGP. So all the routes on IBGP will be uh, considered, the routing table will increase. If there is a flap, those routes. So imagine from the multiple customer point of view. So you're basically interrupting the internet now, right? There will be lot of routes already. There are like 80 lakhs of prefixes in the internet. So unnecessary things has to be avoided. So basically what service provider does is they take all the precautions of solving that kind of issue. And you guys over here, you will not even come to know what are the optimization that the service provider guys are doing in the cloud. Okay, so they will make sure to make use of MPLS. Let's say if the first preference was GRE tunnel, but since they are not gonna support and we ask for something better, they will make use of MPLS. Okay, as I told you, it's not about one extra hop here. Okay, it's about how efficiently they can use this or how optimized they can do their code. Okay, now the traffic reached here, since they are on label, I told you the labels and the IPs are different. Over here they check the destination IP. Same thing with here, it checks the IP. But over in the core it's all about label, so that's why it got it showed as dropped. Okay, and then finally it came to this hop, and from there it finally reached here. So if you see certain tables here, say for example on my core, if I make sure what is my chef table for 1.1.1, it says no route, right? That is why I got this trace route as asterisk symbol. If I do the same command for ipchef 1.1.1, it shows me some output. It's gonna show me my Cisco Express forwarding over here is telling to reach 1.1.1, go via this direction, that is this direction. Okay, 7.1 over on fast Ethernet 0. That's fine. My chef is working fine. But the moment the packet was over here on this router, chef said no route, and I got this asterisk symbol. What happened there in that particular router? What happened there? So I should not see the chef table there. Instead, I must see the MPLS table there. Show MPLS. All right, I guess I have a bad internet today. Okay, so as I told, let's see the MPLS of table now. When I see the MPLS table now, it was not over on the chef. Instead, it was taken care by the labels. Okay, and what is the label gonna say? Label is gonna tell that 2.2.2 and 4.4.4, how are these being connected? Okay, so this is 2.2.2. It's added up with pop label. Now we are gonna check what are these things. Okay, like pop label, swap label. So this is when you're gonna remove the label and forward it. Okay, so what is happening is this core is gonna remove the label and forward to this person, so that this person can send the traffic without label, because this guy is not gonna understand label, so he needs only IP. So that's the work of the core will receive something. So let's say it received on 16, it's gonna send it over on 17, and this router is gonna remove the label and send the traffic, only the traffic. Okay, so over here, so let's see over on the provider end to show MPLS forwarding. See, we are actually making use of the range starting from 16. That's why we got the first label assigned to 16, then 17, then 18, and so on. It goes till this label. Okay, but if you change the range to 100, then might be it starts with 100. Okay, okay, so if you see from provider end 2 point of view, there was a label 17, the outgoing label was 16. So what does it mean? So my traffic, okay, so let's say my traffic, which was being labeled as 16 here, okay, outgoing label as 16 on the interface 1/0, okay, over here. So this is my label that my provider end 2 added up. Okay, if I see the core router, so on the core router I see the IBGP tunnels, that is 2.2.2.2 over here, and 4.4.4.4 here. Okay, and if you see the provider end 1, so what the provider end 1 is going to do, so basically it added 16. From here the label was swapped to 17. Okay, you can see the label now 17, and finally the labels will be taken out. Okay, we normally call it as pop is when we need to remove the label. Okay, so we will remove the label and we will just send the traffic. That's why over here I happen to see the IPs. Then over here I was not able, because that was the time where it reached the core MPLS router, and then it started moving downwards, and we happen to take out the label and start seeing this. So if I do a command over here, for example, show IP chef 1.1.1, if I do the same command on the customer end, let's say this, I get this output, right? Basically what happened is my traffic went from here to here without any label, no label, enterprise router, no label, just on the basis of the destination IP. Okay, same command if I do it on the provider end, you see what happened now. You basically labeled that particular traffic with label 16. So over here, you just label the same traffic with the 16 number. Okay. What happened? The same command when it arrives on the core MPLS. So no route. Okay, that's why you got those trace mark as asterisk symbol, which looked like you totally lost because your chef table depends on your destination IP. Now there is no concept of destination IP here. It works on labels alone. Okay, that's why the chef table failed to give anything. So when I see the chef table, it totally failed. It said no route. So over here you have to check your forwarding table, the MPLS forwarding table, where exactly are you trying to send this traffic. And if you go to provider h1, if you see the same chef table for 1.1.1, you see they have now taken down the label. There is no more label here, no label over here. When you see the destination, there's no label. So it's very clear when it was sent with no label, the first provider router is gonna add the label, the second provider is gonna swap the label to 17, and then the provider is once again gonna take out the label and push it to the destination. Okay, fine. So what are the main components that we involved in this kind of lab design for practicing MPLS? We used IGP. We can make use of OSPF or EIGRP. Okay, service provider have their own protocol for IGP, which is very similar to OSPF, which is called as ISIS. Okay, apart from that, we have also used GRE tunnel, but since we don't use GRE tunnel, uh, we can exclude it, but let me just write it as a overview. We made use of IBGP. Okay, now I'm not talking about the other router IBGP peering. I'm just talking about this versus this IBGP. Okay, so we have the IBGP over here, and finally the MPLS, what we enabled on these interface. Okay, so just few commands, and if you try to validate how the traffic is passing and what are the things happening, things becomes more easier. Okay, let me try to take some capture so I can show you the MPLS headers. Okay, so if you see this packet capture for MPLS, so where is MPLS header been added? MPLS header has been added over here. Okay, it's between your layer 2 OSI as well as layer 3 OSI, right? So the MPLS header has been added in between L2 and L3. Okay, so we normally call this as layer 2.5. Okay, the MPLS we call it as layer 2.5. If I have to just draw it just to represent, so let's say this is my L2 header. Okay, over here comes my MPLS header, and then I have my layer 3 header. So this is how the MPLS headers get associated. Now as a MPLS header alone, what are the different components here? So we have component for label value, which is like 20 bits. Okay. We also have something called as experimental bits, which is 3 bits. Okay. We have something for S is nothing but bottom of stack, and this comprises of like 1 bit. And then finally we have a TTL. This TTL is very similar like your normal ping packets. When you send a ping or when you send a trace route, there will be some TTL value which is used for decrementing by 1 and capture those messages, right? In this case we got something like asterisk, right? Some messages. So yes, the TTL is also part of the header. So this is how the MPLS header look like. This, the first thing is label value, which you're aware that it's gonna add the label of 16, 17 and 18 and so on. Okay. EXP stands for experimental bit. For example, in the case of QoS, you need some IP precedence values on the header, right? So for such kind of traffic, we will have the experimental bit. This is called as S. S is nothing but bottom of stack, which is when you have more than one labels. Okay, I told you MPLS is gonna support multiple services, IP services, IP6, IPv6, IP, Apple Talk, lot of things. So there might be multiple labels. Whatever we saw today was for just one traffic, for a ping traffic, ICMP. But there could be many other traffic as well, right? So bottom of stack, more than one label or something. And TTL, as you know, time to live, which we have in the case of trace route. Okay, and this gets added up in between L2 and L3 header, so we call this as layer 2.5. Okay, so if I show you the header, so over here let me expand MPLS header. So you see here the experimental bit is set to 0. We have the label, we have the bottom of stack, and we have the TTL, which is what we also discussed, the 4 layers or the 4 components of the MPLS header. Okay, so it's clearly visible on the screen itself: the label, the experimental bit, the bottom stack, and the TTL values. Okay. Now we need to understand what are the different MPLS devices that we discussed today. Okay, we have discussed it, but we need to know what are those. Okay, so I'm gonna write it here. So if I just redraw whatever the lab design we have done today, something like this. Okay, we have customer edge, which we call as CE. So what are the customer end here? These are customer end. Okay. Similar way, we have something called as PE, provider end, or provider edge. We can call it as provider edge. So this becomes PE1 and this becomes PE2. Okay. This provider end can also be called as label edge router, because these are the first point of your routers which are either adding the label, and similar way they are gonna remove the label. So we call it as label edge router. Okay, and similar way we have something called as a provider core. Okay, so this act as provider core, And this provider core can also be called as label switch router. This terminology is very important, which we also write it as LSR, label switch router. So basically this is a router which is acting as a transit path. Okay, so the labels are now the packets are forwarded not basis on the destination IP, instead on the basis of labels. Okay, all your label mapping is seen here, and if you ever see the chef table will look like no route. So you have to check what is the MPLS forwarding table or mapping happening here in this case. Okay, so this was the components. Now let's talk about those label point of view. I told you sometimes the label are added up, the labels are removed, labels are swapped, right? So we have three terminology here with respective to the labels. The first one we call as label push. Okay. The second one over here we call it as label swap. And the third one we call it as label pop. Okay, now what is label push? Label push is that first router who is gonna add the label. Okay, so in this case, when I send my trace route or ping table or ping uh, packet, my p router 2 was the first router who added some tag to that or added some label, right? So I can say that whoever adds the first label, we call it as label push. Now, what is label swap? Now, label swap is, for example, I had multiple routers, or let's say in this itself, we got the label as 16, and then we just swapped the label to 17. Okay, like a label forwarding is happening here. Okay, this happens even if I had multiple routers. Say, for example, I had my P2 and P1, and this was my core. Okay, P. But intermediately, let's say if I also had other routers. Okay, I can call it as like P4 and P5. Now what would happen is this router is gonna label it. Okay, this router is gonna make use of swap. Okay, so let's say 16 swapped to 17, provider is gonna once again swap to 18. Okay, and then finally it's gonna be swapped to 19, and finally this router is gonna pop the labels, which we call as pop, the third one, which is nothing but removing the label. So we have the swap in the intermediate routers which are gonna replace the labels. Okay, so swap is a word we use for replace label with a new label, and pop is a word where we are gonna remove those labels and we are gonna send uh, the data or packets in the IP format. Remove the labels because we don't have MPLS in the enterprise level, so we have to remove the concept of label, remove the labels. Okay, three terminology from packet or label point of view. Okay, now there is one more important topic here which we call it as MPLS LDP. Okay, very important topic. This LDP is also called as label distribution protocol. Okay, label distribution protocol. Now this is the topic which is gonna show us how these labels get originated. Okay, so if we talk about these LDP, label distribution protocol, I can just relate them with any of other protocol, like for example your one queue. In case of one queue, you are making use of those ISL and one queue, right? The labels which we added. Similar way, if you talk about ether channel, we have those PAGP, LAGP, that those tagging. Similar way, LDP can also be called as one such protocol. In the case of LDP also, they are gonna send some hello packets. They're gonna form the neighborship or adjacency, right? So in the case of OSPF, let's say if this is my router, okay, I have a link between them. The moment I create a OSPF process, they're gonna send the hello packets, and there are 7 states in the OSPF, and at the end they're gonna form adjacency, right? They work on multicast, the reply comes on unicast, all the other things. The multicast address is 224.0.0.5. The same thing if I say in terms of LDP, LDP is also gonna work on multicast. The multicast IP here is 224.0.0.2. Okay, it is also using those unicast message to form the neighborship. So let's say they send the hello packet on multicast. Once they form the neighborship, the neighbors then are gonna use the unicast to keep the neighbors up and running. Okay, so this is in the LDP process. Yes, there is one more difference in case of these two. Let's say in the case of OSPF, if I put one more link here, okay, so let's say this is 192.168.1.0 series, and this is 2.2.2.0/24. Now what happens is, if I go to the router process on both the router, and if I advertise these both network, they both form neighborship. So you will see one neighborship here, and you will see the second neighborship here. So two neighborship. Okay, but in the case of LDP, even if you have one more route, okay, the second one will not come and act as a neighbor now. That's the behavior. Okay, so they will not form two neighbors, they will form only one neighbor. Even if you have the second link, you have configured the neighborship, you will see just one pair of neighbors only. Okay, so in my scenario, when I just initiated those MPLS command over on the interface, MPLS IP, I showed you one syslog message. Might be I have taken somewhere, and or might be I have not taken. Might be I'll check it over here. So the moment I put the MPLS command, so do you see this syslog message? LDP neighbor change LDP neighbor. So this is acting as your agency now. In case of OSPF, when you form the agency, you get the syslog message saying that OSPF neighbors formed, neighborship is up, and all those things, right? So this is the topic we are now discussing, the LDP topic. Okay, link distribution protocol, LDP. Okay, very similar to other protocol, they are also gonna work on multicast. They are gonna send the hello packet, they are gonna form the agency, and on top of that neighborship is where your packets with labeled will be sent. All the push pop, so swap will happen, and finally we see the MPLS binding in the provider end on the, and in the provider edge side, we will see how the labels get added and how the labels get taken out. Okay, so this is important topic, LDP topic. So let me try to see something over here. So let's open one of the capture. Okay, so we have the LDP packets, hello messages, right? So how do you think the LDP came up? That's because the MPLS generated this, right? So when you have OSPF process, you try to see the logs over on Wireshark, it doesn't mean that it doesn't mean that OSPF in the backend doesn't have any other packet. It will still have those hello packet or keep alive packet keep on running to see if the neighbors are up or down, right? Similar way here, the moment you created MPLS, doesn't matter if you're sending some traffic or something, the LDP has generated and it's doing its work of seeing if the traffic is if the neighbors are up or not. So this is basically a hello message, act as hello message. You see what is happening and to which destination are they being sent. This is a multicast IP. Okay, this multicast IP we also have seen in HSRP version 1. Okay, so this is an IP which is used by multiple protocols. So these are the source, these are the destination, these are the information about it. If you see here, we have the L2 header, we got the L3 header, and then we have the UDP header on top of LDP protocol. Okay, so let me expand this LDP protocol, the hello message. The first important thing here is to know what is the UDP source and destination. Okay, so this is UDP source and destination. Okay, so let me also expand this column. So 646. Okay, the LDP port number is gonna be 646. It's happening between this source and this destination. Okay, and what do we see in the LDP protocol now? So we see this IPv4 transport address 3.3.3.3. Okay, all right, I am almost done with LDP. I got very short topic now. That is with respective to the same LDP, okay, label distribution protocol, but from the data plane point of view. Okay, in the sense, when I did a trace route from the customer end to let's say 1.1.1, source keeping as 5.5.5. Okay, so it is considering some path now. This is some path, right? So we call this kind of table as LDP data plane traffic flow, or I can also write it as LSP, that is nothing but label switched path. Okay, this is the path my MPLS has taken to ping 1.1.1 from 5.5.5. Okay, this is from data movement point of view. If you talk from LDP control plane point of view, we already have discussed what is happening with respect to the labels, how the labels get swapped, how the labels are removed, right? So there are two things here happening. One is control plane, which we just discussed about the labeling, uh, the neighborship, the agency, the multicast, unicast. They were all control plane, which is happening here. But from the data movement point of view, the data plane point of view, which I can see by doing trace route, this is called as link switch path, which in short form I can say as LSR. not link switch, label switch, sorry, label switch path, uh, LSP, sorry, not LSR, LSP, label switch path. Okay. So, well, so that ends this topic. Let me summarize what we discussed. We discussed what is MPLS, where do we use this. Okay. We did a lab on MPLS. We just took a short topology. We discussed how do we lab it. First, we did with the help of GRE, but we know what is the limitation of GRE. Uh, we removed GRE and we configured MPLS. Then once we configured MPLS, we did some troubleshooting and validation to see how this MPLS traffic flow, what are the chef tables that's forming on the customer end or the provider end, and also the code table. Okay. We also checked what are the different labels here. We also checked the MPLS components like the customer and the provider and the provider core. We also discussed what is LDP from both control plane point of view, where we discussed about its adjacency formation and uh, what else about the multicast flow. Okay. And similar way, we also saw the data plane point of view, the traffic when you do a trace route, which shows the exact data flow. Okay, which was also called as the label switched path, LSP. Okay. So what else did I cover? Was it done? Yes. And finally, we had also done something exactly over here, that was to see the MPLS header. Okay. So I told you where does this MPLS header sit. So we have L2, we have MPLS, we had L3. Okay. So this is called as 2.5 layer. And how does this MPLS header look like? The four component of it. Okay. Label, value, experimental bit, stack, bottom of stack, and TTL values. Okay. So from enterprise point of view, this is your syllabus for MPLS. But yes, if you want to read more on MPLS, then the topic is included in the service provider. Okay. If you go with CCNP service provider, you will see this MPLS topic in much more uh, depth, along with the other IGP protocol like ISIS and all other things. I'll give you this topology EVNG. Give me some time to give you the UNL. So basically, it will need the images also. I guess you have the images. They are all on 7200 series. So can I see that startup config? Okay, not here. Yeah, so these are all 7200 which we have used earlier in this topology. Okay, so we were using 7200 on all these clouds. These are all 7200s. So you must have 7200, and apart from that, I have not used any other uh, platform here or other kind of iOS. So I guess if I send you the UNL, that should be enough without any other customization. Alright guys, so let me know if you have any doubts. And yes, I guess we need two more class to wind up. Okay. We need two more class. One is QoS IPv6 and SD-WAN components. So I guess we need three. I mean, we need two classes at least to wind up. All right, guys. So if there is no doubt, we shall meet in the next class and have a nice day and see you soon, everyone. Thank you for joining.